where can we access the graded assignments? So I was told that you all have been enrolled to the, yeah, I was told that you've been enrolled in the workshop course. So there are graded assignments. Did you get any notification uh, for the workshop course? Can somebody please confirm? No, is it? Okay, just give me a moment. Let me cross check. All right, got it. Okay. Yeah, regarding the workshop course, I've asked the team and they will reply and I'll get back to you on that. Okay, can somebody confirm whether my screen is visible or not?
Yes, ma'am, it is.
Okay, thank you. All right, so I request everyone to please mute yourself, and when you have any doubt, then you can unmute and ask the question. Okay. All right, so I hope we can start now. All right. So today, what we're going to start off with is k-means algorithm. So as you might know that all machine learning techniques can be divided into two parts: supervised and unsupervised learning techniques. As you might know, supervised techniques are the ones where we are given the labels for each data point. On the other hand, unsupervised learning techniques are the ones where we only have data points and we don't have any labels for them, right? So what could be the use of a data where there are no labels is what we one may wonder. So in unsupervised learning technique, we look at the data points themselves and we try to see if there are any patterns in them. Okay, there could be several kinds of patterns. In k-means, the kind of patterns that we are looking for are whether there are any clusters present in the data or not, right? So if the data is in 2D, of course you can see them, you can visualize them, and you can see whether there are any clusters present in the data or not, which means there are some data points which are alike, right? So finding out the details about clustering in the data set is what we do in k-means. Okay, so this is what we're going to cover today. I hope everybody is aware of this technique, but still, for the sake of completeness, I would be briefly covering a few theoretical details about this technique in the beginning so that it's refreshed for everybody. And after that, we'll move on to the collab. And I'll start off with some Numpy functions that are going to be used in the implementation of k-means. So that will be some of these could be a brush up for you, and those who are not aware of them, they can learn them, and then we'll move towards the implementation of k-means. So that's the sequence that we'll be following today. All right, so let's start off with k-means. Like I said, there are data points only without any labels, right? So let's say the data points are represented as x1 x2 up to xn, which means there are n data points. Each of these data points have d features, so which means every data point can be represented as a vector in d dimension, right? So I hope you covered vectors matrices yesterday. So here if you look at x1, it will be a vector containing the details of the different features, right? For example, if let's take a simplistic case, weight and height are two features, right? Then weight and height, this will be your x1. Okay, similarly x2 will be weight 2 and height 2, like that. So these are the kind of features here, and d is equal to 2 here, which means the number of features are 2. So this is the kind of data that we have, and there are no labels. So this is all that we have. Now the task is to group them into different clusters based on their placement, right? Based on their values, they'll have some position in the d-dimensional space. For example, here this is 2-dimensional space, so each of the dimensions will represent the features. For example, this dimension will have weight and this dimension will have height, right? So for each, depending on what weight and height a particular data point has, we can plot them here. In 2D you can visualize them, right? Something like this probably. So the motive here is to see whether there are any clusters present or not. For example, this is the kind of clustering that you can see here. That's what we have to identify. There's another term k here, which means we have to partition these data points into k different clusters. Now, what is this k and how do we find that out? We'll talk about that in a while. For now, we'll assume that this k is given. So here in 2D, you can see that there are actually 3 clusters. So k is going to be 3 here, right? But in case of higher dimensional data, you cannot visualize, and hence you may not be able to say clearly what will be the right value of k. So we need to find that out. We'll talk about that. Any doubt so far in the problem description? Okay, I assume. All right, I assume it is clear to everyone what we are going to do here. Now, so here we were able to see in 2D, but let's assume that d is equal to something like, let's say 100, right? Obviously, you cannot visualize. Can you think of how many possibilities are there for grouping n data points into k clusters? Let's say there are n data points and you have to put them in k different clusters. So it's a permutation combination question, actually, a very basic aptitude question.
K power n.
K to the power n. Very good. So how did we get that?
Each there is like k for each
Correct.
there are
For
k.
each data point, so you just take the first data point. This first data point can go to any of these k clusters, right? So there are k possibilities for the first one. If you take the second data point, again there are k possibilities, and so on up to n data points. So k to the n is the total number of possibilities. But note that in such a scenario, it might be the case that some clusters are empty, right? But here this is not what we are going to be doing. So this is an upper limit, right? The actual number of cases, possibilities will be less than k to the n, but you see that there is an upper limit which is k to the n, which is quite huge, right? The actual limit where there are no empty clusters will be somewhere lesser than this, but still this is a huge number, as you see, right? So obviously we cannot do hit and trial. It's an NP hard problem. So in such scenarios, we go for some heuristic. Heuristics means some approximation approach we go for. Okay. Now k means provide one such approach, which is what we are going to look at. Yeah, this is what we have seen. Okay, before we go into what kind of heuristics k means provides, as in the sequence of steps that will be followed, let's talk about a bit about the terminology. So we have the data points x1 to xn, right? Similarly, we'll have z, you can say, z1 up to zn. We will have n more entities which will be called cluster indicators, where we will store which cluster is assigned to a given data point. We need some terminology to record which cluster is assigned to which data point. For example, let's say we have data points let's say 4 data points, and k is equal to 2. So x1, let's say, is assigned to cluster 1, x2 is assigned to cluster 2, x3 is assigned to cluster 1, and let's say x4 is assigned to cluster 2. So we will say that z1 is equal to 1, z2 is equal to 2, z3 is equal to 1, z4 is equal to 2. This is the terminology. We'll be using this in code as well, so it will be good to understand this. So zi can be any value between 1 to k. If k is equal to 2, only 1 and 2 values will be possible for these zi's. So they just capture which cluster is assigned to which data point, that's all. Another thing that we will be using is mean of a cluster. Mean of a cluster and cluster center are one and same thing. So if we use them, you understand they are the same thing. Mean of a cluster and cluster center is one and same thing. So obviously, the cluster for each cluster will have a mean of it, right? And we'll represent that by this mu. Mu of zi is the mean of cluster zi. This is some basic terminology. Now, let's say I give you two, for the given data points, I give you two cluster assignments. One cluster assignment, let's say this is one cluster, this is another cluster. On the other hand, I give you some other cluster assignment, let's say this is one cluster and this is another cluster. So these are two different cluster assignments, right? Now, can you tell which cluster assignment is better? In general, given a cluster assignment, can you tell how good it is? We need some measure to do that, right? So in k-means, this is the objective function which tells us how good a given cluster is, where we try to minimize the distance of each data point from its cluster center. Now, how is this going to be useful? Let me give you an example. Let's say this is one cluster, this is another cluster, and we have a data point. We want to decide which cluster this should go on. And let me also highlight the cluster centers. Let's say these two are the cluster centers. Now, this green data point, which cluster this should go to? Should this go to this cluster or this cluster? Would anybody like to tell me?
The right one.
The right one. Why did you say this? Why? Because we see the distance of this data point from this cluster center, and we see the distance from this cluster center, and we see that this is smaller. So we make this data point a part of this cluster. So that's our that's our strategy, and obviously it makes sense, right? The data point should go to that cluster whose cluster center is nearer to it, and by doing so, we are actually minimizing the distance of each data point from the cluster center that it is part of, right? And this is precisely what we are representing here. For each data point, this is the mean of the cluster that they are assigned to, this is the distance between them, and this is the square distance. Sum of all these square distances we are trying to minimize. So firstly, you understood why we are doing this. This makes sense, right? A data point should be assigned to a cluster whose center is closer to it, right? And in doing so, we are trying to minimize this objective function, as you can see. So this is the target in k-means, right? Now, in order to do this, we follow a particular strategy, which is what we are going to discuss now, and which is what we are going to implement also today. K-means is also called Lloyd's algorithm, okay? Now, there are in particular three steps that we follow in k-means. First is initialization of cluster centers, okay? So some data points will be given to you, right? Some data points are given to you. Let's say these are the data points. You will randomly initialize some cluster centers, right? Let's say you call that this is one cluster center, this is another cluster center, this is another cluster center. This is random, okay? There is no strategy that you use here. So k means initializes cluster centers randomly, okay? Once that is done, so in doing randomly, actually it could be something like this also, right? Because this is random and there's no strategy that we're using. So these could be the cluster centers initially. That is followed by initial assignment of data points to cluster, which means for each data point, this is what we are going to do. Let's say this data point. We will find the distance of this data point from first cluster center. We'll find the distance of this data point from the second cluster center and from the third cluster center. Whichever is closest, as you see, this one is the closest. That means this data point will be assigned to this cluster center, right? This step we are going to do for each of the data points. Let's say this data point we take. We'll find the distance of this data point from this cluster center and this cluster center and this cluster center. As you see that this one is closest, so this data point will be assigned to this cluster center. We do this for all the data points. Now this is initialization. This is one step, which is initialization. We will implement this also. So we have so far discussed this one. Now, as you see that some data points will be assigned to some cluster center, probably something like this, right? After this, what we do is we compute the means of all the clusters. Now, as you can see, these data points are assigned to, this cluster center. We need to compute the mean, and this will be updated. This will be not this. As you know, some data points have been assigned to this cluster now. If you compute the mean of all these data points, it'll be somewhere over here, probably here. Similarly, you'll compute the mean of these data points somewhere over here, that will be, and the mean of these data points somewhere over here. Now you see that your cluster centers have been displaced. Earlier, these were the cluster centers. Now these are the cluster centers, right? Once again, what you will do, you will check for each data point whether they're happy in their cluster or not. I'm using an informal sentence here, but that will make sense to you. So what I'm saying is, after you find the new cluster centers, once again, for each data point, you will check whether they're happy or not, which means, are they in the cluster whose cluster center is the closest to them? Okay, this is called reassignment of data points to clusters. Okay, which means for this data point, you'll check whether this is closest to this cluster center or not. As you see, this is closest. So this will say that this data point is happy, which means this data point will not move in this particular iteration, right? We check this for each data point. So if we find a data point whose cluster center is not closest, for example, this data point you see, if you look at this data point, the distance from this one and these ones, this distance seems to be the closest, which means this data point is not
करने
happy in
का
its own cluster.
लेकिन उसको तो डेटा निकल गई थी रात
Can
में 3
can
को दी
everybody
मैथ है
please mute? Can I request everyone to mute, please? Yeah, so you see that this data point is closer to this cluster center rather than its own cluster center, which means this data point is not happy, hence it will move to this cluster in this particular iteration. So in every iteration, some data points will change clusters. Okay, those data points which are not happy. Okay, so we are going to repeat these two steps again and again, which means there'll be reassignment of data points, and hence there'll be recomputation of the cluster center, which will change, right? And once again, based on the new cluster centers, we will do the reassignment of data points. So these two steps are going to repeat until convergence. Now, what is convergence here? Convergence means when in a given iteration, no data point changes their cluster, right? That means the cluster centers are going to remain the same. So that is what is called convergence here. Now, how can we be sure that whatever sequence of steps we are going to follow here, whatever we just now discussed, is that going to converge or not? Can we say that? So there's a proof behind that, and I'll not get into the details of that proof. I'll just briefly cover that just for the sake of completeness again. But these steps that I'll tell you, this will make you understand that this algorithm is actually going to converge. Now, the algorithm that we just now discussed, I told you, only those data points will change cluster that were not happy, which means their distance from some other cluster center is shorter than their distance from their cluster center itself. Okay, which means they are closer to some other cluster center which they are not part of. Okay, and hence they will change cluster in this given iteration. Now, can somebody tell me when given data point changes cluster, the value of objective function reduces or increases?
Reduces.
Reduces.
Reduces. Very good. Very good. It reduces. So in every iteration, the value of objective function is going to reduce. Why? Because a data point is going to go to a cluster whose cluster center will be closer to it, right? So the value of the objective function is always going to reduce. Now, one more thing to note is that whenever any reassignment happens, which means a data point changes cluster, it will result into a new partition, obviously, right? Now, in the very beginning, we discussed what is the upper limit on the number of partitions. We discussed this, k to the n, right? Which means maximum these many number of times only reassignments happen, which means the maximum number of iterations that can take place in k means is k to the n. This is an upper limit, as we saw, where the clusters are expected can be empty also. So the actual number will be much lesser than this. So there's an upper limit, as we know. There's a finite upper limit. So this cannot go on and on. Why? Because the number of partitions after every reassignment, the partition will change, right? A new partition will come, right? And also we know that the value of objective function is also reducing. So what we are saying here in the proof that it can never go beyond k to the n. That is the upper limit. Actually, k-means in practice is found to converge in the first few iterations. Of course, it depends on the data also, but in general, it converges much before this. Okay, so we do not even need to go up to this. So this is about why it always converges. Now, initialization cluster centers, right? I told you that in k-means, the cluster centers are assigned, initialized randomly, right? So if these are the data points, it could be the case that randomly these data points are chosen as the initial cluster centers, which doesn't seem like a good approach. With time, they will actually move, right? With time, they will actually move here, but that may take longer time, right? On the other hand, if let's say we had chosen the cluster centers to be here, here, and here, then the k-means would have converged quickly, right? So sometimes you might want to go for an intelligent strategy to initialize the cluster centers. So k-means does this randomly, but there's one more approach which is called k-means plus plus, which can be used to initialize the initial cluster centers. Can you please mute everyone? Okay. So k-means plus plus uses an intelligent strategy to initialize the cluster centers. That's all. Everything else remains the same. So whatever sequence of steps we discussed, everything is same. It's just that here instead of random, the here the first step will change. Everything else will remain the same. So only initialization will be affected in k-means plus plus. Now I'll again tell you briefly about this k-means plus plus strategy to initialize the cluster centers. Do you agree with this part? Cluster center should be as far apart as possible, right? This
Yes.
makes sense, right? So here, like
Yes.
I told you two cases. In one case, all the cluster centers were close by. In order to displace them to their actual positions, it might take longer. Um, so it will be good if they are far apart as possible. So that's all k-means plus plus tries to do. So what it does is it chooses the first cluster center uniformly at random. So let's say these are the four, let's say 5 data points. So k-means plus plus will randomly choose one of the data points out of these, right? Let's say this one. So each will have same probability, which is 1 by 5. So let's say it chooses this one. Now the next second cluster center that it has to choose, it makes sure that that cluster center is as far apart from this one as possible. For example, you see the distances of each of the data points from this one. This one is as far apart as possible. So this is more likely to be the second cluster center 1, cluster center 2, and so on. So these two have been finalized. Now it will go for the third cluster center. Again, that should be as far apart as possible from these two cluster centers. So that's the strategy that k-means plus plus uses. Okay.
Ma'am,
Yeah.
ma'am, how would
Yeah,
the
go on.
third center is taken, ma'am? Third center.
Third one, right? Okay.
Yes.
So these C1 and C2 are finalized. Now the third one has to be chosen. The third one has to be chosen. So what we will do is, for each of the remaining data points, we will see the distance. For example, let's see this one. We'll see the distance of this data point from first cluster center and the second cluster center, right? Now you look at the maximum, so minimum distance you see. So this is the minimum distance, right? This is what you will record for this data point. Okay. Similarly, for the next data point, let's say this one, you will see the distance from the two existing cluster centers. Again, minimum of these two, let's say this one, you will record this. And for the third data point as well, you will find the distance from the two existing cluster centers, and you look at the minimum of these two, you see that minimum if this is this, right? Now there are three distances that you have. You will take the maximum of these. Okay. So the maximum is this one, as you can see, right? This one. So which means this data point will be the third cluster center. Okay. So if you are taking the maximum of the minimum distances, right, that makes sure that this data point is as far apart as possible from the existing two cluster centers. Is this clear?
It is clear, ma'am.
Okay.
I'm sorry to interrupt you, but in one of the revision session, you told to take the minimum distance.
No, minimum, maximum of minimum. Yeah. Is this what you mean? Maximum of minimum. So if the minimum distance is this much and you're taking the maximum of that, that means this data point is as far apart as possible, isn't it?
Actually, I got confused, but I have to recheck. But as far as I remember, like it was in quiz one revision session, you said that if the distance between like 3.5, 10, 20, and 30, then you were taking 10 over there. If I'm
10,
able to
no, 10 is minimum, right? And we have to make sure that the next cluster center is as far apart as possible. So this part is clear, right? It has to be
correct.
maximum, right? Now maximum it has to be, that is one thing. Now if there are multiple cluster centers which have been chosen initially, now what do we do about them? So let's say this data point, if the minimum is this much and we are taking a maximum of this, which means the distance, the distance has to be as far apart as possible. This minimum distance is what we have to maximize, isn't it? Okay, you can take an example of max and it will not make sense, right? Because minimum distance will be somewhere lesser than that, right? For example, I'll give you an example. So let's say there is a data point and minimum distance is 5 and the maximum distance is 50. Okay. And you're recording the maximum distance, which is 50 here, right? And then for the other data point also, let's say minimum was 6 and the maximum was 55. And here the minimum was, let's say, so what example do I want to take? The You want to, okay, let's say this is 60. Okay. All right. Yeah. So these are maximum distance, okay, for each point, which are the candidates to become the next cluster center. Now you take the maximum of this, the maximum is 60, and you declare that this should be the next cluster center. But you see, the 1 is the minimum distance, which means this data point is at distance 1 from some cluster center. Do you want this to become the next cluster center? Yes? No?
No.
Yeah, correct. This data point has distance 1. You don't want to want this data point to be the next cluster center because it is very near to some cluster center. That is why you are recording the minimum distances to make sure that every data point is far apart as possible from all the existing data cluster centers, right? Does it make sense?
Yes, ma'am.
You do one thing, you take a few examples and it will become clear, and probably you can follow this very example and it makes it clear.
Okay.
I think he's talking about the assigning the scores to the data points, because then that will be the
Scores will be proportional only. Scores are proportional only, right? Scores are
yeah,
proportional to distance.
yes,
Okay.
yes.
Yeah, doesn't matter. All right, one last point we'll discuss about k-means and we'll move on to coding part. So initially
Ma'am,
yeah,
ma'am, can I ask one theory question?
yeah, go on.
So, ma'am, I didn't understood the k-means algorithm like second and third step. Like, what are
Okay,
we modifying in those steps? So,
okay.
in first step, like we have taken the cluster centers that I
Hmm.
understood, and
Okay, see, these were the random cluster centers that we assigned,
right,
right?
right, right, right,
Now obviously they are not correct cluster centers, so we
right,
have
right.
to gradually reach towards uh, the correct cluster centers. How do we do it? So it uses a strategy which is actually kind of a greedy strategy, but it tends to work. So what exactly it does is, for each data point we check which cluster center they are closer to, right?
Okay.
Whichever cluster center they are closer to, they are assigned to that cluster. We
Mm-hmm.
do this for all data points, right?
Mm-hmm.
At the end of this step, every cluster has some data points which have been just now assigned to it, right? Now you compute the mean of that cluster. How do you compute? So let's take an example of weight and height, right? Let's say 30 20 is the first data point, this is the second data point, and this is the third data point, right? Let's say these are the three data points which are assigned to cluster 1. So you will find the mean of this cluster, right? Whatever that comes out to be, divide by 3, whatever that comes out to be, right? This is the mean of the cluster C1. So which means the cluster center which was earlier has been now displaced, and a new cluster center will be now emerging, right? Is this clear so far?
Yes, ma'am.
Right. Now once again we have to check whether every data point is closer to their cluster center or not. For example, in this cluster, whatever data points were there, we have to check whether they are now closer to this new cluster center or not. If they are, then we don't do anything. Okay, if they are not, for example, yeah, this data point is in this cluster, but if you see the distance between these two, this data point is actually closer to some other cluster center and not its own cluster center, which means this data point needs to go to this cluster, right? So we do the reassignment. That's what we were talking about. We do the reassignment of each data point. If the data points are closer to their own cluster center, good. If they are not, then they will be moved. Now this data point will move to this cluster.
So, ma'am,
Is this clear so far?
ma'am,
Yes,
one
ma'am. Got
question.
it.
Yeah.
So, data center need not be one of the data point, right? It can be any, like
Yeah,
any.
it may not be. It may not be. Initially, it will be the data points because that's how we're going on. The data points will be chosen as the initial cluster centers. But later on, as you compute the means, obviously, they will not be any of the data points. They'll be somewhere in that particular region. Okay. Is
Yes,
this clear so far?
Ma'am,
Okay.
ma'am,
Now, just one question. Yeah. When
ma'am,
you move
suppose
this, yeah, go on.
suppose a point is equidistant distance from all the centers, then
In
in
that
which
case,
case?
randomly one is chosen. Randomly one is chosen. Okay.
Okay,
Yeah.
ma'am. Okay.
Now this data point, when it moves to this cluster, now my question to you, will the mean of this cluster change or not?
yes, ma'am.
Yes,
Yes.
right? Yes,
Yes.
correct. Now, after all the data points have moved to different clusters or stayed in their own cluster, which means after some reassignment, the cluster centers are going to change, correct? Is this clear to everyone?
So, ma'am, is it as a reassignment with replacement, something like that? Like, say, we assigned one point to one cluster center and again mean changes, or firstly we reassign all of them and then recompute?
All of them. So, in one iteration, every data point will be treated. Okay?
Okay.
Yeah. Clear to everyone? So, let's say in one iteration, we have checked each and every data point, and they have either reassigned, and they have either been reassigned or they have stayed in their own cluster, but some reassignments have happened. So after these reassignments, obviously, if you compute the mean of each cluster, that is going to change. Like I showed you, it is going to change, right? Because the data points will be different. Yeah. Yes.
I just want to clear my understanding. Okay.
Mm-hmm.
So first, the 30, 20, 20, 10, 10, 10, these 3 points, these are in cluster 1, right? So
Yeah.
we calculate the mean of that 60, 40 by 3, 20 something. Okay. Then from that 20, we are again taking the Euclidean distance, right?
Correct.
For each
Correct.
point.
Yes.
Each point.
Yes.
And
Each point.
each point. Then we are taking the minimum.
Yes.
Right?
Yes.
Okay. So, okay. Then, okay. From every, then this is like from every cluster, we have to take Euclidean distance every iteration. Is it correct?
Yes. Correct. So in every iteration, for each data point, you will compute the Euclidean distance from each of the clusters. Okay. Whichever is closest to them, you record that this data point should be assigned to this cluster, and you do the reassignment.
And ma'am, you told it will converge. Like why it will converge? Like after some iteration.
Yeah, that's what. So in every iteration, so let's say there was an iteration 1 and some reassignments happened and new cluster centers were formed, and based on that, you once again computed which cluster should be assigned to each data point in second iteration, and so on. Now, can you tell me what will happen to the value of objective function? Objective function, we have discussed this one, which is the distance from the cluster centers. Can you tell me anything?
Reduce.
It
will
will strictly
gradually
reduce, right?
Yeah.
It will strictly reduce, or it will remain the same in some iterations, right? After some time, let's say no data point moves from one cluster to the other. Everybody is happy in their own cluster, which means everybody is closest to their own cluster center than any other cluster center, right? So in that case, objective function will remain the same and there will be no reassignments. That is when it is said to be to have been converged. Okay, and we discussed the proof briefly, that the value of objective function is going to reduce, and every reduction in objective function returns into a new partition, and there is a limit on the number of partitions that can be there, the total number of possibilities that we saw. It cannot go beyond this, which means there'll be at some point of time there'll be convergence that will happen. Is this clear?
Yes, ma'am. In K-mean plus algorithm, you told in the initiation, when initialization, we're taking the cluster center as far as possible, as far apart from. Why? I mean, why far? Like I didn't understand.
Yeah, so it is to converge quickly. Obviously, if okay, let's again revisit this example. Let these blue plus points are the initial cluster centers, right? They are all very close by, whereas they should have, one cluster center should have been here and another should have been here, right? So they are close by. In order to shift them to their correct place, it is going to take a lot of iterations, isn't it? Right? So, but if they are as far apart as possible, it is quicker to converge, right?
Okay.
It makes sure that all the cluster centers are not lying together, right? They are they're likely to be near the data points to which they are ultimately going to be assigned, right?
And ma'am, in MLT course, we have been taught like hard clustering or soft clustering, as far I remember.
Yeah.
So it's hard clustering, right?
This one is hard clustering because for each data point you only assign to one cluster, right?
Okay.
Okay, now we have to quickly move on to coding, but before this we'll discuss this.
Excuse me. Yeah. So in K++ algorithm, this choosing of the cluster means as far as possible from each other. It will be done only at initial
Yes.
stage.
Yes.
And after that, it will go like earlier.
Yes. Only
And
this
there
will
was,
change.
yeah. And one more thing I remember, professor has taught that I don't remember that in K++ or somewhere else, some probability should be linked with
Right.
I mean,
So
some
this is
score.
so
What
what
was
I
that?
told you right now was deterministic, right? Which means whatever whichever data point is as far apart as possible will become the next cluster center. But actually, it is probabilistic, which means the distance works as the probability. Distance is proportional to the probability. If the distance is more, that data point has more chance to be the next cluster center. If the distance is smaller, that data point has lesser chance to become the next cluster center. So it is probabilistic. So that helps in proofs, as in it guarantees that we'll get on an average we'll get the best initial clusters. Okay, so
Right.
you can simply convert the distances into probability, not a big deal, right? If the distances are 20, 30 and 40, that's what we saw. You can just 20 divided by 90, and this is your probability, right? So with these probabilities you will choose those data points to become the next cluster. That's all. Don't worry about that. Okay?
Yeah.
All right, so choice of k. Initially I told you that k is something that we have to decide. K means will not do something and give you the best value of k. It's not like that. K is an input, which means k is a hyperparameter which has to be provided to the algorithm. It is not a parameter that will be computed by the algorithm. Now, how do we find what may be a good k, given that we are not able to visualize the data and we may not have any idea about k? So how do we go about? I'll just give you a brief idea and we'll move on. Now, let's say there are a few data points, n data points. Let's say I assign k to be equal to n, right? Can somebody tell me what might be the value of objective function in this case?
0.
Very good. Why? Can somebody explain?
Because if each data point is its own cluster, then the distance will be 0 only.
0, right? Distance from the cluster center is going to be 0. So the value of objective function is going to be 0 in this case. On the other hand, if I assign k is to be equal to 1, can we say something about the value of the objective function?
Pretty high.
It will be very, very high, right? Every
Outliers,
data.
outliers will not.
Sorry, what are you saying about outliers?
There will be points which are farther that might not be proper, right?
No. When I say k is equal to 1, even outliers, everything will be part of one cluster, right? Everything will be one cluster when I say k is equal to 1, and hence actually the presence of outliers is going to increase the value of objective function to a much higher value. So it will be a very high value, right? And what is our motive here in k-means? The objective function value should be how much? It should be minimized, right? Yes?
Yes.
Now here we are getting objective function value to be 0, but is it of any use? No, right? Because
No.
every data point is in their own cluster. We are actually not able to find any pattern. This is of no use to us. So the value of k should be somewhere between 1 and n, right? Between 1 and n. Somewhere, which is what we have to get an idea of. Okay. Now in practice, we use something called elbow method. I'll briefly tell you about it. So what we do is we try out different values of k. Okay. We try, let's say, starting from 2 up to some value, let's say up to 10, depending on the data, of course. Let's say 2 to 10. We apply k is equal to 2 to the data and compute the value of objective function. Similarly, we apply k is equal to 3 to the data, we compute the value of objective function and so on. Okay. Now, can you tell me about anything about how these objective function values will increase or reduce, or is there any relation there? As the value of
Will
k
reduce.
increases, correct, right? I hope this is clear to everyone. As the value of k increases, obviously there are more cluster centers, and obviously the distances are going to reduce. The values of objective functions are going to reduce. So what we do in elbow plot, on the x-axis will be k, and on the y-axis will be the value of objective function. And as we know, the value of objective function is going to reduce. Now, when there is some inherent clustering present in the data, like this is actually, there's some inherent clustering with k is equal to 3 in the data. When we move from k is equal to 2 to k is equal to 3, you will find that there's a huge reduction in the value of objective function. On the other hand, when you move from k is equal to 3 to k is equal to 4, obviously the value of objective function will reduce, but it will not be huge reduction. Why? Because there is no inherent clustering in the data. Let me explain that why that will happen. So k is equal to 3, something like this will be the clustering, and when you introduce one more cluster, so there'll be one more cluster center, and hence the values will reduce. But since they are so close by, the value of objective function is not going to reduce much. So that's something we observe in the elbow plot. Something like this might be observed. So when you move from k is equal to 1 to k is equal to 2, there'll be huge reduction, because you actually get to identify the clusters that are present. Similarly, when you move from k is equal to 2 to 3, there'll be more huge reduction. But when you move from 3 to 4, some reduction, but that'll be very small. So it'll be something like this, sort of linear. So this is the kind of elbow, and that indicates that 3 should be the correct value of k. Okay, so that gives you an idea. All right, so I hope this background detail was clear to everyone, although it has taken a good amount of time. Now we should quickly move on to the code. Any doubt?
Yeah. One question, ma'am.
Yeah.
Like regarding the elbow method.
Go on.
Let's suppose that because we have just tried between 2 to 10, and for simplicity we have taken like elbow is forming at 3 only. Is it possible when there are like a large number of data points, then there can be 2 elbow or 3 elbow instances? So is it possible?
So you take the last one, okay? You take the last one.
Okay.
After that last point, there'll be sort of a linear reduction. Obviously, at 2 also there is a huge reduction, but you take the last one, which is 3, okay?
Oh, no, I'm talking about the elbow thing. So like within the same data set, if I take like, let's say, if I extend this elbow diagram to more than 10 data point, 10 clusters, there will be like 2 elbows are forming or 3 elbows are forming. Then in that case?
That is a little unclear scenario. That will happen in the case when there is not a good clustering, right? So something like this. Obviously, your data could be a little random, right? So in such cases, you might observe whatever you're saying. In that case, you will decide based on some domain knowledge. The domain knowledge will actually help you to decide what k value you should take. For example, there was a project that I was working on. There I was identifying 3 kinds of people: voters, questioners, and answerers. I knew that there are 3 kinds of properties in everybody. So I that's why I took k is equal to 3, although there were some 2 values of k which were kind of possible there. But from the domain knowledge, I understood that this should be the right value. So that in those places you might have to take some decision, okay?
Okay.
Based on some knowledge about the data.
Okay.
All right, we'll quickly move onto the code, and I'll first cover some NumPy functions, the important ones, which we are going to use in the implementation as well. So I'll import NumPy. I hope you all have been introduced to the basics yesterday. So one function that I'm going to start off with is numpy.random.choice. So whatever function we are going to do, in case you have already come across, will be revision for you. Else you should note how they work. Yeah.
So we have to do coding in this same collab, or we have to open another one?
I've actually kept a copy in the folder that has been shared with you, but I think you may consider doing it later on because that will take longer time, right? We have 1 hour, 10 minutes, and you might focus on what I'm doing right now, and you might want to practice later, but it's up to you. Okay. In this collab, you can work whatever I've shared in the folder. Is that
Can you share the link of the folder in the chat?
all right? So numpy.random.choice. Everyone, please mute yourself. So if you pass a number in numpy.random.choice, it will give you a number randomly between 0 and that number, which is 10. Here, 0 to 10, it will randomly give you a number. I execute this again. I get another random number, and so on and so forth, right? Multiple executions of the same statement are going to give me random numbers between 0 and 10. Okay. Let's say I want multiple random numbers between 0 and 10. I'll mention the second parameter. Let's say 20. Now I got, so this 20 is for size. I got 20 random numbers between 0 and 10. Okay. This is how random.choice works. Another version is
0 to 10 or 0 to 9?
0 to 10. I guess you can check this, the documentation, whether the last number is included or not. You can check out the documentation and you can check here. If the last number is included or not, please check that out.
Okay.
Okay, so another version of random.choice is when you pass an array as the first parameter instead of an integer, numpy.random.choice, let's say I create an array. Okay, this array I create, and that array I'll pass here in numpy.random.choice. What it will give me? A random value from this array. Okay, this is the second version of random.choice. Once again, if you want multiple numbers, you can pass the second parameter to indicate that I want multiple numbers, multiple random values from this array. Please note that there were 6 elements here and I got 10 out of this. That indicates that these are with replacement, which means it is not that every number will come only once. The numbers can be repeated. This is with replacement. Okay, this is random.choice. Next is numpy.random.seed. I'll be using this to generate the data set. So this is random produces a random output, but if you want to make it sort of predictable as in you get the same value across different runs, you can make use of numpy.random.seed. For example, if you we've seen that. Yeah. When you execute this again and again, you get a different value, right? So if I execute, I get some value. If you execute, you get some other value. But if you want that all of us should get the same value, then before this, I might write numpy.random.seed. Some seed I can pass. Now, no matter how many times I execute, I will get the same random value. So that is used if across different runs we want the same result.
What is the significance of this 0? Means we can change this number to
you can
any
pass
integer.
Any value you can pass.
So is
Because
it
you
the
get the different
probability what assigning to that number, or what is happening there?
Okay, so so the random numbers that are generated by computer or any programming language, a function in any programming language, they're actually not truly random. That's why they're called pseudo random numbers. Probably you would have heard of. So there's some algorithm that is used inside when you call any random number generator. Some algorithm is used and there's some seed value that is passed. Okay, so when we pass the seed value, this seed value is used in that algorithm to generate the random number. Okay, so since an algorithm is being followed and it is not truly random, that's why it is called pseudo random number generator. Okay.
Okay.
Okay, next we'll see numpy.random.randn, which is connected to normal distribution, standard normal distribution. Can somebody tell me what is a standard normal distribution? Probability.
What's the significance of that semicolon?
Mean will be 0 and standard
Standard
deviation.
deviation 1 and mean is 0.
Okay, one by one. So semi-comma not needed. You can write it like this also. One and same thing. Okay. I'm just combining these two, so I put this. You can do simply like this. One and same thing. Okay. All right. So numpy.random.randn. Yeah, standard normal distribution is one which has. Can somebody tell again?
0 mean and variance of 1.
Right. 0 mean and variance of 1, right? So when I call this function, I get a value from a standard normal distribution, which means, like you said, which will have mean 0 and deviation 1, right? Which means most of the values will be closer to 0, either positive or negative. So here we got minus 0.89, which is close to 0. So the probability to get the values closer will be high, and the probability to get values away from 0 will be low. So very less likely that you will get a value which is quite far away. So that's the standard normal distribution, and it's sometimes used to generate noise in the data that we sometimes generate for any ML model. We will use it today. Okay. All right. So one more version of it. Here we got only one number, right? If I use numpy.random.randn and I pass the dimensions of the array in which I want the numbers to be generated, let's say I pass 10, 2. Then I'll get a 10 cross 2 numpy array of these values. So which means I got multiple values as per the size of this array, which I will pass, whose dimensions I'll pass here, whose shape I'll pass, not dimension, whose shape I'll pass. So 10 cross 2 is the shape I want. So I got multiple random numbers generated. Okay. Next is numpy.random.randn. So there are several variants of random numbers. You should know which one to use in which scenario. For example, if I use numpy.random.randn, I'll get a random numpy.random.randn. I'll get a random integer between 0 and 100. You can check whether 100 is included or not. Similarly, if you want multiple numbers, is one more variant. So the size, you see, which is optional. If you don't pass this size, you get 1. So let's say I pass 0, 100 and let's say 5. Right? So I got 5 numbers between 0 and 100. Okay. All right. So we'll use this also in our implementation. Next is numpy.arange. When you want to generate numbers in a given range, you will use this function. For example, I pass a number here. That number will be taken as stop. This is the sequence that we follow. The start is optional, step is optional, stop is what we'll pass. If you pass only one number, that will be taken as step, starting from 0. And this definitely goes up to 10 minus 1. Okay. So 0 to 9, which is 0 to 10 minus 1, these numbers will be generated. So here 0 to 11 and so on, right? So here we did not pass any start value. So start was taken to be 0. We did not pass any step value, which is the gap between these numbers. So by default, that is taken to be 1. You can mention explicit values for them. For example, if I write 10 to 20, I'll get numbers from 10 to 20 minus 1, 19. By default, the step was 1. So if I give another value, the third parameter, that will be taken as the gap. So these values will be generated. I hope this is clear so far. Any doubt?
This array range will definitely give the integers only, or
Yes.
we can also get that like linear space, some point values.
Yeah, linspace gives you points equally spaced, which may be fractional also. Here you get integers only. In case you want fractional values, so you can multiply them with the fraction. So in one scenario, I wanted fractional values, so I multiplied them with, let's say, divided them, each of these values by 10. So you can further perform that next step, but it generates integer values. Okay.
Excuse me, ma'am. It will create the floats also, ma'am. Display the floats values also.
It creates. We can let's just check the documentation. Evenly spaced values within given interval. So okay, let's check
Yes,
the
ma'am. It creates
step
the
values.
float
Let's
value.
check
Yes.
this value. So 0.2 if
1.1
you.
or something.
All right, it works. Okay, fine. Okay. So at some point I wanted, I don't know, that maybe it depends on the version that I was working on. So I remember I had to multiply all the values, divide all the values by some value to get them in a given range. Anyway, so good, it works for floats also. All right, so you can use that. Okay. Any doubts so far, or shall we move on to the further functions? Okay. Now let's see this numpy.concatenate. It is used to concatenate different numpy arrays. Okay. Let me show you the basic syntax first. I'll create a numpy array and one more. Okay. Let's say I want to concatenate these two arrays, which means I want to create another array which has the elements 1, 2, 3 as well as 4, 5, 6. Okay. So I'll write numpy dot concatenate. Inside this, I'll pass a tuple containing the arrays that I want to concatenate. So when I do this, I get an array which has values 1, 2, 3 and followed by 4, 5, 6. You can assign it to some new array and then you can continue with that one. So this is basic concatenation. Now there's one more parameter in concatenation which you should be aware of. So there's something like access, which is quite important for several numpy functions. The value of access is by default 0 for concatenate function. Okay. Now what does that mean? Access 0 means first access. Okay. And then access 1 means next access, which is second access. So if it is a 2D array, access 0 will mean the first access, which is rows. I should give you an example here probably. Okay. Let's say there's a 2D array. Okay. What is the shape of this 2D array? Tell me.
2 by 2.
2 by 2.
Cross 2, right? Okay. Let's say this one. Yeah. This is the 2D array. What is the shape of this? 3 cross 2, right? Okay. In a 2D array, access is equal to 0 will mean this and axis 1 will mean this. 0 means number of rows and axis 1 means the columns. This is axis 0, this is axis 1. Okay, so in several functions this axis might be required. There's a default value. In many cases axis 0 is 0 default by default. In some functions axis will be none by default, so we'll have to be careful of what is the default value. So here axis is 0, so it will concatenate along that axis. Okay, so let me give you an example of a 2D array and then it will become more clear. One more thing to note is that when we are doing concatenation, we should be aware that the shapes should be compatible for concatenation. Okay. So what is the shape of first array A1?
3 cross nothing. 3 cross 1.
3
cross
comma
1.
1, right?
1.
Sorry, 3 comma, right? This is
3
the
comma.
shape, right?
Yeah.
3 comma.
This is the shape of the first one, and
It's 3
the shape
columns
of
or
A2
3
is
rows, ma'am? 3 columns or 3 rows?
Same 3 comma.
3 comma means this is a vector, one dimensional thing. Okay, if it had been a 2-dimensional thing, then it would be 3 comma 1. Okay, this is a 1-dimensional thing, this is a vector. When it is 3 comma 1, this is a matrix actually. Okay, so A2 is also 3 comma. Now I want you to note this thing. Firstly, all the input arrays must have the same number of dimensions. Here the dimensions are same, that is one thing which is matching. One more thing, the arrays must have the same shape except in the dimension corresponding to the axis. Let me add another element here and let me try concatenating them. I'm able to concatenate, right? The shape of the second one is 4 comma. Note this point. The arrays must have the same shape except in the dimension corresponding to the axis. Here the default axis, which was 0, which is this one. Here if it doesn't match, doesn't matter, but rest should match. Here actually there is no rest, right? So it doesn't matter in this case. Let me give you an example of a 2D array and whatever
Hello,
what
ma'am.
I'm saying. Yeah.
Here when I put that x is equal 1, so it is throwing an error because it is not 2D.
Because there is no axis 1. Is there any axis 1?
Yes,
Here?
but yeah, but how can we like keep those two columns side by side? I mean 1 4 2 2 5 3 6 like that.
Okay, for that you have to convert it into 3 comma 1, this one, and 4 comma 1, and now there's a 1. So now it will not be a vector, it will be a matrix. Okay, and after you convert the shapes to be 3 comma 1 and 4 comma 1, now there is this axis. Firstly you have to make sure that this is 3, right? Because this should match, only then you can.
Yesterday in the workshop, Karthik sir, explained all these things. It was there.
Okay.
Reshaping and all. Yeah.
All this was there. Okay, good. So then it might be clear to you. Concatenation was covered or not?
Yes,
Yeah,
ma'am.
yeah,
Completely.
Oh, concatenation was covered. Oh,
Right,
good.
right.
Yes, ma'am.
All right. All right. Good then. So I'll quickly move on.
I
Just
think
this.
concatenation was not there. Stacking was there. Column
Okay.
stack and yeah.
Yeah, actually there are multiple functions to stack or concatenate different arrays sidewise or lengthwise. So these are different possibilities. This concatenation I find quite straightforward, so I stick to this one, but you can go with any one. So I want to demonstrate another axis example and then we'll move on. Okay. Now if you see these two arrays, the shapes are like this, right? Now let me concatenate them. Numpy.concatenate. Please note that we'll put an extra pair of round brackets here, and then I'll pass B1 and B2. Okay. Now if I Let me print this result as well as the shape of this result. Okay. So the shapes, please mute yourself if you're not speaking. Okay, so 2 cross 2 are the shapes of each of these. By default, what is the value of axis here? 0. That means that axis will change after this concatenation operation. You might want to note that point. So after we concatenate, we get the shape to be 4, 2, which means the axis is equal to 0 value is going to change after the concatenation. Okay. Now let me try out one more thing. If I say axis is equal to 1, what happened? Can somebody explain? Please mute yourself. Whoever is not speaking, please mute yourself. Okay. Yeah. So now I'm passing axis is equal to 1, and axis is equal to 1 means column wise, right? Which means the second thing in the shape, and that is going to change. So earlier the shape was 2 cross 2, 2 cross 2. Now after the concatenation, this second value is going to change, and that is what happens. And in order to put that in effect, the elements will be put like this: 1, 2, 3, 4. So 1, 2, 3, 4, and the second array 5, 6, 7, 8, it is put like this, and hence the resultant shape is 2 cross 4, which means the axis is equal to 1 got changed. Okay. So these are different possibilities. You may want to explore this, and since it was covered yesterday, I'll move on. Numpy.linearalgebra.norm is what we are going to use it, and it is used to get the length of an array. Okay. So numpy.linearalgebra.norm, if I write, and let's say I pass this, it gave me the length. How did you get this? Square root of 1 square plus 1 square, which is square root of 2, which is 1.414, right? So it gives you the length of an array. Similarly, can you tell me what we will get here? What we might get here quickly?
5.
Very good, right? So this function is used to get the length of a vector. Now I want to just add that it can also be used to get the difference between, the length of the distance between two vectors. Let me create two arrays, and let's say I want to find the distance between these two arrays. So I can simply write numpy.linearalgebra.norm. I want the norm of a minus b. A minus b is the distance between a and b, and I want the length of that distance. So this is how I'll get it, right? So if you want to do it manually, you can do that also. You can use square root function. Square root of what you want? You want the square root of 1 minus 3 and 2 minus 4, right? So you can write 1 minus 3 square plus 2 minus 4 square. You square root of that, right? You want this some bracket by dot square root
Extra bracket at the right.
Should not be.
I put extra bracket. This one, okay. Yeah. So if you see, both these values should be equal. Let's see. I want to see both values. Right. So in order to do something like this, you can simply use numpy.linearalgebra.norm and the distance and a minus b. That will give you the distance between two vectors. Now another some basic function which will be required is numpy.argmin. Okay, let's say I have this array. Okay. Now, if I write numpy.min, what I might get? What I might get here?
Minimum of
minus 10.
minus 8.
Minus 10, right?
Minus 10.
On the other hand, if I write argmin, numpy.argmin of a, what I might get? Argmin give the index of the minimum value. That's all. Okay, just keep that in mind. We'll be using this also, right? So minimum numpy.min will give you a min value, and argmin will give the index of that minimum value. That's all. Okay. I hope you are aware of append function in list. I just want to add that append you can use here also in NumPy. So let's say I have this. I want to append, let's say 8 to this A. So I am able to append this 8 at the end of this array. So in list, it was like L dot append 8, right? In NumPy, it is like NumPy dot append A comma 8. One thing that I want you to note is if I print this value of A now, I see that there is no change here, right? Which is surprising because we appended 8 to it. So I just want to highlight that numpy.append creates a view. There are several functions in NumPy and also pandas which do not make changes in the original copy. They generate a view. Some of them have this extra function in place. In place is equal to true when by default it is false. But when you set in place is equal to true, then this 8 will be appended to the original copy of 8. There's no in place here. So what you can do is you can write like this. A is equal to numpy.append. By doing this, that change will be made to A, right? So in code, if you use it, you should be mindful of writing this. If you don't do this, then you will not get the result that you were expecting. Okay.
Ma'am, this can be used at places in exchange with concatenate, right?
In concatenation, you're concatenating two arrays. Here, you're just adding an element, right? These are two different use cases, right?
I have a difficulty.
Yeah.
You had in argmin, it is written about flattened value. Axis, it is flattened. No,
Which
if
one?
axis is flattened, np.argmin. It is written if axis is none, the array is flattened first. What does it mean by array is flattened first?
Okay, let me give you an example. Okay, so let's say I have an array. This flattening will make sense only when we have 2D array or more than that, not in 1D array. So let me take a 2D array and then it will become clear. Let's say, okay, let's say this is our array. Now, if I write numpy dot argmin b, okay, I leave it here. If I do numpy dot argmin b, and that's all. What has happened? Would anybody like to tell me? Any guesses?
Is reshaping the array.
First reshaping the array into one dimension and taking
Yeah,
the min.
correct.
Yes.
So the default value, axis value is none for argmin. And whenever axis is none, the array is first flattened, which means any dimensional array is converted to a one dimensional array. So here it is 2D array, so that will be flattened and it will become 1, 2, 4, 3, 8, minus 5. That will be 1D array after flattening. And the minimum value is minus 5 and the index of that is going to be 0, 1, 2, 3, 4, 5. Right? That's what we are getting. Even if you pass this it won't make any difference. Here, sorry, here we have to pass. It's the same thing, right? But the difference will come in because it's a 2D array. The difference might come in when you pass some other axis. For example, when I pass axis is equal to 0. Now, what is the shape of, let me write this. What is the shape of the? Shape is 3 cross 2.
3 cross.
When I pass axis is equal to 0, that means this axis, which is something that is 3. Now, 1, 2, 4, 3, 8, 5. Right? So let me show it here. It will be more clear. So 1, 2, 4, 3, 8 minus 5. Right? Now, axis is equal to 0 means this 3 pertaining to this 3, which means this thing, something that has 3 values, and this thing, another next thing that has 3 values. Now, what is the minimum of this? Minimum is 1 and its index is 0, as you see, right? And here the minimum is minus 5 and its index is 0, 1, 2. Okay, this is what we're getting here, 0 and 2. So when you pass an axis in case of 2D
Can you
array,
repeat this, please? Can you please repeat?
Yeah. So it's a 2D array. So axis will make sense. Axis could either be 0 or 1. When we pass axis 0, that refers to the first axis, which is 3 here, which means 3 means this is an indication that whatever thing has shape 3. Okay, so here columns have shape 3. So you will find the minimum of this separately. You find the minimum of this separately. Minimum of this is 1 and the index is 0. Minimum of this is minus 5 and the index is 2. So that's why you get 2. Let me show you axis 1 and then it will become more clear. So when you pass axis is equal to 1, see what happens. So axis 1 means this one, 2. Something that is 2. Now, this thing, and this thing. What is the minimum of these? 1. And the index is 0. Minimum of these is 3 and the index is 1. Minimum of these is minus 5 and the index is 1. So you get 0, 1, 1. This thing, right? So you should be aware of these axes. They are used in several functions and you should be mindful of using the right axis. Okay, and flattening, when you don't pass any axis, all this will be flattened. Yeah, that is straightforward. Is this clear now?
Yeah.
Okay.
Ma'am, can I ask one off-topic question, please? In real world, there are millions of record, right? Millions or billions. So that time, these additional computation, right? Like say flattening, sorting of the data to get the mean and all. So that becomes like say quite computation intensive, right?
Yes,
Takes a lot of time
I
to
mean, it depends on
get
if
the
your data is huge, these operations will take more time. Although Numpy is faster as compared to something like list, right?
Yes, yes.
Many times faster, like at least 50 times faster Numpy is. But still, if your data is huge, definitely it will take some time, right? Okay. Numpy.mean, quickly, it's actually similar. So let's say this is the array and we apply numpy.mean. Okay, we'll have to compute means. So let's clarify the understanding of this function. So obviously, if it is a 1D array, it's straightforward, nothing to see there, right? But if it is a 2D array, let me take this one only. This is a 2D array, and when we apply mean here, what will happen? Okay, once again, if you write numpy.mean and b, okay, by default the axis is none. It's a 2D array. By default the value of axis is none, which means it will flatten the array and just will take all the elements and will compute the mean of them. That's what you're getting here. But if you want mean across any particular axis, which may be a more useful scenario in a 2D array, you will have to pass the appropriate value of axis. For example, if I pass axis to be 0 here, right? Let's see what happens. Numpy dot mean is what I had to write, numpy dot mean, right? So axis is equal to 0 means this thing, something that is 3. Once again, it will compute the mean of this and will compute the mean of this. These two values will get. Let me make it a little easier to understand and see what values you are getting. Let me make this to be the array. The mean of 1, 2, 3, 4, 5, 6 is 3.5, right? The mean of this, so what is happening here? 1 plus 3 plus 5. 9 divided by 3 is 3, right? 6 plus 4 plus 2, 12 divided by 3 is 4. So column wise, right? So axis 0 to 0 means this thing 3. These three values put together, and the mean of that. On the other hand, if you take axis to be 1, right? Now axis 1 means this thing, this two things. These two values taken together, 1 plus 2, mean of that is 1.5. 3 plus 4 is 3.5, 5.6 is 5.5, right? So whenever it's a 2D array and you have to compute the mean, you should be mindful of which axis to use. Now, a follow-up question to you. We have discussed k-means and we computed mean. I gave you an example of mean, right? There were data points and you had to compute the mean of that, right? In order to compute the cluster center, obviously you will find the mean of all the data points here. Can you tell me what should be the appropriate axis here?
1.
0 equal to 1.
1.
0.
0.
0.
0.
0. This will be 0.
1.
It will be
1.
0. 0.
Yeah.
0. Right? It will be 0. Right?
All rows should go together and all columns, means other values should go together, right? So that is
Let's
1.
say there are 20 data points. Let's say there are 20 data points, x1, x2 up to x20. And there are two features, right? D1, D2. These are the values. So 20 cross 2 will be this is your feature matrix X. This 20 cross 2 is going to be the shape of your matrix. Now, axis is equal to 0 means, first thing, 20, these 20 taken together, mean of that will be here. These 20 taken together, mean of that will be here. Okay, we'll take it up in a while again, and probably this will be more clear. Now, I think broadcasting would have been discussed yesterday. I'll just give one example because I will be applying it. Let's say we have this 2D array and another 1D array, let's say. If I write this, what will happen? Just want to check. What will happen if I do this?
It will add 1 to the every row.
Row-wise addition.
Row-wise.
Row-wise addition, right? This 1, 1, 1 will be added to 1, 2, 3, and 1, 1, 1 will be added to 4, 5, 6, right? This is the broadcasting that will happen. We'll be making use of that in a while. Okay. Now we'll see accessing array elements. I hope you are clear with that. So let's brush it up. Let me create an array. Let's say this is an array. If I want to access its first element, what do I write?
X0.
Right? Simple. If you want to access the first element, you do this. If you want to access the, let's say, first 3 elements, what do I write?
X0 to 2, 0 colon 2.
2 is it?
Column
3.
3.
Column 3.
So you might
2.
be aware of slicing in lists. Okay, that you can apply here also. That works in a similar manner. Now, my follow-up question. Let's say you want to access first element and third element. What do I write?
Step size.
Comma.
0:3, then comma 2.
Why 0:3? I want only first element and third element. Should I write like this?
This will work.
More array 0 to.
One more array, is it? Like
Barabar.
this?
Yeah.
Very good. So just note that if you want particular elements at different particular indices, you have to pass those indices inside a bracket. Okay, so if you do like this, you will get an error. You have to pass a list to access the particular elements that you want. This is one way of accessing the array elements. Now let me show you one more. If I inside this, if I pass an array containing some true and false values, then wherever the value is true, we'll get that value. Wherever the value is false, whichever index has false value, that value will not get. This is yet another way of accessing particular values from a Numpy array. Is this clear to everyone?
And that double square is not clear. Can
Yeah,
you please repeat?
Internal array length should be same as that of
should be
array
same.
size.
Correct. The internal array length should be same. If you do not pass an extra bracket, you will not get anything. So make sure you pass a list of Boolean values inside the subscript of x, the brackets of x. Okay, you have to pass the array, and like somebody said, the length should be same as the number of elements in the array. Okay. Now let's move on to. So we have pretty much covered the several functions that we'll be using in implementing k-means. Now it should be a little easier for you to understand. So we'll start off with generating the data. For k-means, we could actually use some libraries from sklearn. For example, make_blobs is one library that can be used to generate clustering data. But it'll be good if we generate ourselves so that you get comfortable with that part also. Okay. Now, since you have seen this, can somebody tell me what we'll get here? If you remember.
Two random numbers between 0 to 10.
No, it's standard normal distribution.
Random normal
Dimension.
Okay. Very good.
Matrix.
It's a dimension 10 cross 2.
Dimension is
Right?
10.
10 cross 2 is the dimension of the resultant array that we'll get, and every value will come from a standard normal distribution, right? All right, very good. Now, let's say I add something to it. So we're just putting the pieces together. We're just connecting the dots that we have already seen. Okay. Now, if I do this, what will happen?
You just add a noise to
Add
the
10,
whole
20 to every.
addition. 10 and 20.
Broadcast? Did somebody say
Yes.
that? Or okay.
Yes, broadcast.
Yes, 10 and 20 will be
Correct.
added to that.
10 and 20 will be added to every value. So kind of the values got displaced by 10 comma 20, isn't it? It's like that, right? All the values that were there in this particular array, they got displaced by 10 and 20. All right. We're going to use something like this. Firstly, I'm going to set a seed so that we get the same results. Let me generate some data points, 2000 data points I'll generate. Now, I'm going to generate data that will have 3 clusters. Okay. So, I want to generate the data randomly from a standard normal distribution. So, numpy.random.randn is what I'll use. I want that roughly 1/3 of the data points should pertain to one cluster, 1/3 of the data points should pertain to the next cluster, and so on. So this n we have decided to be the total number of data points. So if I do n by 3, which means 1/3 of the data points, And let's say I want 2 features only because I want to be able to visualize as well. So I'm on purpose keeping only 2 features. So this is what I'll write, and divide by 3. Now one more thing, if I do 2000 divided by 3, I'll get a float value. So let me put a double divide here in order to get a floor value, integer value. This is what I want to generate. So 2000 divided by 3, whatever that comes out to be, those many data points will be generated. Now I want 3 clusters. So they should be displaced by some value, right? So I'm going to pass some values in order to displace these data points from other cluster values, from other cluster data points. This 2, 2 I'm passing, that x value should be shifted by 2 and y value should be shifted by 2. That's all I'm doing here. Now this is one cluster's data. Similarly, I'll create the rest of the 2 clusters data as well. And let me displace them by some other values. You can try out, experiment, play around. I'm just putting in some values in order to have 3 clusters at some positions from each other. That's all.
What is seed doing here? I'm not getting.
This random is there, right? If I run these statements once, I'll get some values. If I run these again, I'll get some other values, right? And so on. Similarly, if you run, you will get some other values different from what I get. I want everyone to get the same values, and I want different executions of this code to give the same results. Is that clear?
Excuse me, ma'am. Is there
So
any
for
difference
every
between the random state 42 and random dot cd seed 0?
Yeah, random state 42. Random state you use in a particular function. You probably would have used in MLP, right? Some library, right?
Yeah.
So that applies to one that function. Okay, random. So here this random seed is applying to all these 3 functions, right? Is that clear?
Okay, ma'am.
That's kind of
Yeah,
local.
instead
This
of
is kind of
0,
global. Yeah.
if it use the 1000 in the seed
You
value,
can use
seed
anything.
function,
You can write your birth date here. Anything you write. Okay.
is there any significant difference of value if we use different value?
It is the initial value that is passed to the algorithm that generates the random values in Python. You can look that up if you want the inside details of how a random value is generated in Python. Okay. So there's a particular algorithm that is followed, and one seed is provided, and this is we're trying to have control over that seed. That's all.
So, ma'am, this seed will work for only one cell. Means whatever we are.
One cell, correct. One cell. Okay. All right. So we got this data for 3 clusters. Generally, we want to keep all the data points in a matrix, which we refer to as feature matrix, and we generally denote it by X. So let me put everything in this matrix by using concatenate. Okay. Okay. So I'm going to just concatenate these values, and this X is what I'm going to further work with. Let me see what is the shape. So 2 got lost because we converted them to floor. So it doesn't matter. This is so 1998 are the data points that we have with us. Now let's, since it is 2D, we can visualize them. Let me import. Yeah.
Like the first step which you have done in the above step,
Sorry.
like you have taken empty array 2, 2 minus 3 and minus 3. Like you have taken the random values, right?
These ones?
Yeah.
These are not random. This is what I've given. I mean, these are, you can say, arbitrary values. You can give any values here. You can give 12, 12, whatever. Let me visualize it, and then it will become more clear as to what exactly happened here. Okay.
Okay.
Okay. So I want to represent 1 point for each data point. So I'll use plt.scatter. On the x-axis, what do I want? I want. So this is my x, right? I want
all the data points.
All row and
rows, 0 value,
0,
and
right.
I want all rows and 1 first column's value. in the y-axis. So this is what I want. So this is the kind of data that got generated. Now you were asking me about these values. Yeah.
This data point has like the mean is different, but the variance are same, right? Because we are just adding like for the data 1, data 2, and data 3.
Correct. So initially when you compute this data, you know that mean is 0 and variance is 1, right?
Yeah.
And when you displace them, then the mean changes, variance remains the same. That's what is happening, right?
Yeah.
So yeah, somebody was asking me these values 2 by 2. So you know, let's say something got generated here, then I displaced it by from x-axis by 2 and from y-axis by 2, like this. So this is the first cluster, as you see. Similarly, then other set of values I displaced by -3 and it came up over here. The next one is -5 3 and this is the one. So you can try out different displacements and you can see how the data changes. Okay.
The resulting mean should be like what we have displaced in those value, right?
Yes, correct. Okay. Now, as you know, getting back to
We have
k-means.
used seed is equal to 0. It will. It means that over the random values will, once generated will remain the same throughout, right?
Yes.
Okay.
Yes. Okay, getting back to k-means, you remember the 3 steps. First is initialization of cluster centers. Second is reassignment of the data point, assignment of data points based on these cluster centers. Third is recomputation of cluster means, right? These are the 3 steps that we have to implement. Now let's start with k is equal to 3.
Ma'am, can we say that we already know the means like 2, -3 and -5? So this will means converge to those means only.
Okay, you assume that you don't know anything about this data. Now, this was just to explain to you that you can generate the data like this.
But it will go there only, no? Since we know
Yeah,
here.
it will correct. It will converge to those values only, close to those values. Okay.
Okay.
All right. So now we have to. So there are 1998 data points. We have to randomly choose 3 out of them, and those 3 should be the cluster centers. Okay. So numpy.random.random.randint. Randint expects low and high values, starting and ending values, right? And it'll give me a random integer in that range. So 0 to 19, you can write 1998, or if you want to make it a generalized code, we can write x dot shape 0. So x dot shape will give you 1998 comma 2, x dot shape 0 will give you 1998. How many random values do I want? We want k is equal to 3, so we want 3 initial cluster centers. So I'll pass size is equal to k. Let me show you these values. Print random indices.
I think we should add seed also, right?
Seed also, yeah. So we can add seed also, or you can also manually give these values, but yeah, in order to make it generalized, it's a good idea to give a seed value. So these are the cluster centers that we are getting. Now let's these are the indices of the cluster centers that we are getting. The exact cluster centers will be these data points from the feature matrix, which is X. So these random indices I'm going to pass to X, and those will be our cluster centers. Cluster centers are data points, they're not indices, please note that. So these are the 3 cluster centers. This is the first cluster center, second and third. Okay. Just to give you a little more idea. Go on.
Since these values are flattened, that's why we can simply access it by the one index, right? Otherwise,
No, they are not flattened. No. in the x, this will be 0th value. This is first value. This whole will be second value. Is that clear to you?
Yes, yes, yes.
So we want which value? 684th. So going by this, wherever 684th value is, that will be returned. Is that clear?
Correct, correct.
Okay. So let me visualize the cluster centers as well. So this is how we visualize the. Any question there?
Yeah, ma'am. Basically, we have taken the random values over there. Like we have taken three values of the centers. And now, because you have taken them randomly, and now you will apply the KNN right
Yeah.
right after this. Okay.
Yeah.
Hello. Yeah, ma'am. Hello. Screen. Yeah.
It's the same for everybody. We just lost connection with her.
Yes, yes, yes.
Hello, am I audible? Hello?
Yes.
Oh,
Yes, ma'am.
Yes, ma'am.
when did you lose me?
From 10 minutes.
10 minutes, is it?
Yes,
Yes,
10
ma'am.
minutes.
Okay. Oh, I don't know. Anyway.
We
All right,
were
I'll
doing
share my.
the visualizing cluster centers part.
Okay, no problem. No problem. Don't know what happened. Anyway. Okay, let me know when you see my screen. Okay, got it, Samanyu. The sharing is taking time.
Ma'am, this collabs will be available or not?
These are already there, I think, in Drive.
I mean, they're filled up,
No, these collabs will not be filled up for individual.
We can do exercise, I think.
Okay.
The screen is visible, ma'am.
Voice, is it?
Now we can hear you.
You can hear me?
Yes, ma'am.
Okay.
Yes.
All right. Let's quickly get back here. So I hope you saw this visualization. So these are the centroids that are the initial centroids. Now the next step is to assign each data point. So we have assigned each of the data
This
points.
part you need to explain.
Actually,
I think we are a
can.
little ahead. We had just mapped the clusters and also the centroids in the initial state. And I
Right.
think
So
this
this is clear, right? This part is clear?
No, ma'am. This was
no.
not explained.
Visualize the cluster centers as well. That part was.
I think you have to go a few more up
Go up.
the program.
This was done, right? So this was done, right?
No.
No.
From
Okay.
here, I
We
think.
just started
No,
on.
even
Okay.
this was not done.
No.
We just
This
started
was
on
done,
No,
right?
cluster
ma'am.
centers.
No, ma'am. Yeah, this is.
Ah, yes.
After the
So,
initial
All
cluster
right.
This is
center.
it.
Okay. Okay. All right. Okay. So these are the initial cluster centers. And what do we have to do now? For each data point, we have to check which cluster center is closer to them, right? So whichever cluster center is closer to them, that is the cluster that they will be assigned to. And we are going to record this information in this Z array. Okay.
Ma'am,
So
sorry to interrupt. Can we start with the previous cell?
yes, ma'am. Because that, yeah, this one.
Yes, ma'am.
Yes.
visualization, is it?
Yes.
Okay. So this visualization you would have seen earlier also. I'm just now I'm visualizing the cluster centers as well by using this plus. These are some attributes from plt.scatter that I'm using. I just want them to be visible enough, so I'm increasing the size and I'm changing the color. That's all. So these are the 3 cluster centers that were formed, and you can see that they are not at good positions. All right, so we want k-means to handle this. We want k-means to bring these cluster centers to the right positions. Okay. Now, how do we do that? How does k-means do that? For each data point, it will find the distance from each of the 3 cluster centers. Whichever distance is the least, that is the cluster that gets assigned to the data point, right? So that's what we are doing here. We create an empty array, Z array, and inside that we'll record the closest cluster index, right? How do we do that? So like I said, for each data point we have to check. So I'll start a loop for each in X. Okay. Now I have to compute the distance of each data point from each of the cluster centers. And how do we compute the distance? I told you numpy.linearalgebra.norm. A minus B gives the distance between A and B. Here A and B are what? The data point and the cluster centers. And how many cluster centers? There are 3 cluster centers. So we want 3 distances here. So I'm using a list comprehension. I hope you're clear with that. List comprehension from Python course. So numpy.linearalgebra.norm, I'm finding the distance of each of the data points from each of the cluster centers. So inside the list comprehension, I'm starting this for loop from I to from 1 to k. So if you see this is what we're going to get. So for each data point, we are getting a list where the distance from each data point are recorded. Okay. Now, whichever distance is the least, that is the cluster that gets assigned. So here, for example, 5.6 is the least. So first cluster, which is 0th cluster, should be assigned to this data point. So we have to record that also. And how do we find the index of the least distance?
Argmin.
By using numpy.argmin, right? So this is what we are going to use now, numpy.argmin from this list. That will give us the cluster that should be assigned to this data point. So if you see this, this is what we'll get. 0 or whatever cluster is closer to each of the data points, 0, 1 or 2 values we'll be getting, right? 0, 1 or 2 values we'll be getting. Now we have to store this detail. We were here, right? We have to store this detail in the Z array so that we can refer to it later on. So we just append this chosen cluster to this Z array, which was initially empty. So ultimately, this Z will contain all the clusters that should be assigned to each data point. Okay. So after this, since this is a step that we'll be performing again and again in each iteration, I am putting this in the form of a function. This function I've created, all the instructions are just the same. Identify cluster of each data point is the function that I'm creating because we'll be needing it later. Yeah, this function we'll call it later. Now I want to show you which new clusters got assigned to each of the data points. So I'm visualizing once again by plt.scatter. Everything else is same. I'm just adding this one thing here. I want that every data point should have a color based on whatever cluster gets assigned to it. So C is equal to Z is what I'm doing. C stands for color, and the Z is the, as you know, contains either 0, 1 or 2. So if it is 0, it will get a different color. If it is 1, it will get a different color, and so on. So these are the, so initially these were the, yeah, here there is no clustering. After, as per the initial clusters, these are the clusters that got formed. Now, this is one cluster, as you see, this purple one, and this plus you see, plus is the initial cluster center. Now, as per the new data point that got assigned, this plus should be displaced here, right? Which means this cluster center has to be recomputed, right? So the next step is going to be compute updated cluster centers. How do we compute the cluster centers? We have seen that. You take all the data points from, let's say, cluster 1, and you find the average of them. That's all. Okay. Now, your feature matrix X has some data points belonging to cluster 1, some data points belonging to cluster 2, some data points belonging to cluster 3. In order to find the mean of C1, you have to take only these data points. In order to find the mean of C2, you have to only take these data points, and so on. How do we do that? Okay. So what is happening here? This statement, can you see what is happening here? I'm passing an array of true values, isn't it? So x dot shape, as you know, is 1998, right? So 1998 true values are being passed to it. So can you tell me what is happening with this statement? Hello, am I audible?
We are getting all the values because
right, we are getting all the values. Very good. Now let's say I put a false here. What will happen?
None of them.
None of the values, right? Correct. Now let me change it a bit. Okay, if I do this, what will happen?
Only if remainder is 0.
Not
Only the
remainder of
odd
index.
Even.
Yeah.
Even it is false.
Even false and odd. Odd is true. So only the values present at odd indices is what I'll get, right? Now, one more thing I want to show you. Let's say I write this. What will be the effect of it? This Z is an array, Numpy array, which has some values 0, 1, 2, right? Now I'm putting a condition, double equal is for condition, as you see. When I do this 1 will be checked for each value of Z. For first value of Z, is it 1? No, then it will be false. For the next value, is it 1? No, it will be false. For the next value, is it 1? Then the result will be true. It's like that. Similarly, if you write Z is equal to 2, only those values which have 2, which are 2 in Z will be true. Similarly, if you write Z is equal to 3, only those values where there is a 3 will be true and the rest would be false. Now you can make use of this Boolean array that is returned by this statement. So if I write this inside list comprehension, I'm creating this list. So can somebody explain me what is happening here?
It will put
Creating
like
separate
all the
clusters.
cluster.
We get 3 rows in that list with true false.
Right. So what we are getting is x z is equal to 1. So let me show you an intermediate step also. So if I do this x z is equal to 1, right? I will get those data points where z is equal to 1, right? All those data points which are a part of cluster 1. When I write z is equal to 2, I'll get all those data points which are part of cluster 2 and so on. So when I write x z is equal to I for I in range 1, 2, 3, I get those data points. So I get 3 arrays. The first array should have all the data points belonging to cluster 1. The second array will have all the data points belonging to cluster 2 and so on. Okay, three separate list. This is list, right? So 3 separate lists I will be getting. Now, how do we get the means of these? So you know that numpy.mean is for getting the mean of those values. So I'm just I'll write numpy.mean x z is equal to I. Please mute yourself. Axis is equal to 0 or I in range. Okay, so I'm actually doing the same thing. Just I'm adding numpy.mean here. Yeah. So this thing you saw. Now I'm computing the mean of this. And I'm just passing an axis to be 0 because we know that we want to mean like this. The sum of rows, the mean of rows. That's what we want. Now, if you see this, these are the 3 updated means that we were looking for. Okay, so again we have to again and again compute the updated means, right? So I'm going to put this in the form of a function so that we can perform the rest of the iterations easily. Compute cluster centers, let's say, and I'll pass x, z and k. These are going to be the cluster centers. I'm just copy pasting here, and those cluster centers will be returned by this function. Okay, these cluster centers will be returned. Let me call this function to check that everything is working fine. Okay. Yeah, let's see. Yeah, so we have created a function to compute the cluster centers. All right. Now we have to keep performing these two steps again and again. We have computed the cluster centers. Once again, what do we have to do? For each data point, we will check which cluster center they are closer to. If they are not happy, right, then they will be reassigned. So that's again, that's something that we have to do again, which is being done by this function, identify cluster of each data point. So once again, we'll execute this function. And after that, we'll once again compute the cluster centers. And after computing the cluster centers, we'll again check. So these two steps are going to be performed again and again by k-means. So we can set some number of iterations for now, because it's not a bad data, it's a comparatively clean data. As we see, there are 3 clusters which are clean clusters. So I'm going to start 10 iterations. And what do we have to do in these iterations? Cluster centers have been recomputed. For each data point, I have to identify their clusters. So this function I'm going to be calling in the iteration. Let me also plot the result so that you can see what is happening. So these two, again, I'm going to copy so that you can see the effect of each iteration. And once the cluster is identified, once again, we will compute the cluster centers, the updated ones, right? So we're just performing these two steps again and again. And since I want to show you the plots, the intermediate plot, so I'll write plt.show here. Let me also print the cluster centers that get created. Okay. plt.scatter list indices. Okay. Where are we passing the tuple? Okay. plt.scatter list indices must be integers or slices, not tuples. Okay. Cluster centers are these. Cluster centers are these, right? So these are cluster centers.
Function cluster center is written in the form of list, ma'am.
Yeah, this is list. That's what. Yeah, this is a list which is not required, or maybe we can have it in the form of an array only, because initially cluster centers were in the form of an array. So that will be good. We will. That is for the sake of uniformity. Cluster centers were initially an Numpy array, right? So we can do this, and let's see. So yeah. So these are the different iterations. Since it was a clean data, k-means was able to converge even a couple of iterations, right? Within 1 or 2 iterations, it converged. So these are the intermediate results, as you can see. After the second, this is the second iteration, and these are the cluster centers, and they are not changing because everybody is happy in their own cluster. We are running for 10 iterations and there's no change because it converged very quickly. You can try out with the bad data, you can try out with bad initializations, and this is what you can explore further. Okay, so any doubts?
Not calculated, right?
Objective function value we are not computing. Yeah, we are not computing. You can do that.
Please explain the initialization part once again.
Yeah. So initialization, as I told you, there are 1998 data points. You can randomly choose 3 of these data points to be the initial cluster centers. Okay, that's what we are doing. How are we doing that? We are using numpy.random.randint. So here there are 0 to 1998. There are 1998 data points. So we are passing low to be 0 and high to be x dot shape of 0, which is 1998. And how many cluster centers do you want? K. So you can either write k here or you can write size is equal to k, one and same thing. So k as in 3 random indices will be given. Now, if you look at the X matrix, it will be something like this, right? So if you write X0, that will be this data point. If you write X10, that will be this data point, and so on, right? Here we want X1289, X1149, X527. That's what we are doing. Okay. So we are
passing distance computation part.
Okay. So distance, I told you, numpy.linearalgebra.norm we can use. And we want to find the distance of each data point from each of the cluster centers. So you can actually do it one by one. You can write numpy.linearalgebra.norm each minus cluster centers 1 and store it in some list. And then find the distance from 2 and store it in that list. And from 3 and store it in that list. I'm just clubbing that using list comprehension by having this for loop. Okay. So we got the distances. Now, whichever is the least distance, that is the cluster that this data point should be assigned to. For that we are finding using argument. Okay. So that we are calling a chosen cluster. And this very
result
detail.
Will be, yeah, Z will be the next set of
cluster centers.
Clusters,
correct.
Clusters assigned.
Clusters assigned, correct.
Okay, so after the total iteration, Z will be the completely next set of cluster centers for each data point.
Yes, correct. You can actually try out printing the values of Z, or it's a huge data point, data set.
Yeah,
you can start with a small data set and then you can see what is happening. Okay.
Okay. Got it. Thank you.
All right. Any other doubt in whatever we discussed?
If we do the real iteration, so that time we can stop if values start matching for cluster center, right?
Definitely, you can do that. Are you able to see my screen?
I mean, is it not a good
Yes,
idea
ma'am.
to calculate the objective function? And
you can do that, but okay, let's say you want to find the value of k, right? Here k is equal to 3 is what we are passing. Let's say you want to experiment with different values of k. In that case, in order to have the elbow plot, on the y-axis you have the value of objective function. You will have to compute the value of objective function. You can do that, right? How would you do that? For each data point, you will find the distance from their cluster center and you will square that up and you will sum that up. That will be the objective function value for a given k value. If you want to draw the elbow plot, you will compute the objective function value for different k values. Okay, you can do that. But here it is not needed.
Okay.
Yeah. All right. I hope it is clear. So now you have another session at 3, right? So I'll stop it here. And yeah, so yeah, I'll close it now so that you get a
can
good
we
break
get the
before the
collabs,
next session.
Field collabs like this?
Collabs you'll get after 21st. So okay, once again, you didn't get any notification about the course portal, is it? Workshop portal?
Ma'am, yesterday 6 collabs we got.
No, not that. The
No,
assignments
no
that you have to
details.
perform.
No,
Okay.
ma'am.
Okay, I'll look into it. I'll ask the team to share the details with you. Okay. All right. So you have to submit the assignments by 21st, and after that you'll get all the collabs.
Okay.
All right. Okay, so you have another session at 3, so you get a good break before that. So I'll close this session now, and I'll see you again sometime.
Hello, excuse me, ma'am.
Yeah.
Yeah. In the meantime, we didn't cite on the how you done in the collab. So how can we solve on our own self? We don't available your notebook.
Notebook I've shared, but that is empty. You will have to put in the code there. So I hope you get the recordings of this. I mean, you get it on YouTube. So you can follow that along and you can fill in that collab. The collab is empty. The questions only, the topics are there. If you see in the folder I shared. So you have to fill that in. The collab containing all the code will be shared after 21st. Okay.
Okay, after the assignments.
Yes.
Oh.
Yes.
Thank you, ma'am.
Thank
Yeah,
you.
okay.
Take
Thank you.
care. Bye, everyone.
Kindly share the
Thank you, ma'am.
assignment quickly.
Thank you. Yeah.
Thank you, ma'am.
Yeah. Bye. Take care.
Thank you, ma'am.